welcome to the next video. So in this video we're going to review chapter 7. Okay, so open your textbook to page 371. Okay, so on page 371 is where chapter 7, Applications of Integration, starts. So in 7.1 is areas between curves. So we learn how to compute the area between curves in 7.1. Right, so let's say you have a graph. Okay, so here's the x-axis, here's the y-axis, and so let's say you have a curve looking like this and a curve that looks like this, and then an interval from A to B. Okay, then area between curves would be the area of this shade region here. That would be one example of finding the area of a region S between curves. Okay, and so on page 372, number 2, it tells you the equation for that. So the area A of the region bounded by the curves y equals f of x and y equals g of x, and the lines x equals a and x equals b, where f and g are continuous, and f of x is greater than g of x for all x in the interval, is, so the area of that is capital A equals the definition from A to B of f of x minus g of x dx. Alright, so we use that equation to find the area between curves like this. Alright. Okay, so that's the equation to use. And so we'll go over a few examples again in this video. So 7.1 is using that equation. The next section is 7.2, which is on this equation. This equation for 7.1. Okay, so now going to 7.2. 7.2 is on volumes, so how to calculate volumes. Alright, and that starts on page 376. Okay, so we use a special shape called a cylinder in order to calculate volumes. On page 378, it gives the definition of volume. Now, mainly, the equation we will use to compute volumes is this equation. The capital V equals the definition from a to little b of capital A of x dx. Okay, where capital A is the cross-sectional area. Okay, and so we'll use that equation to calculate the volume. Okay, of three-dimensional objects. All right, and so we'll see there's several different methods you can use for that. Right, there's the there's what's called the disk method. The disk method is when the A of x is the area of a circle. Okay, and there's the washer method, where the A of x is the area of a washer. You could also have the volume equal definition from C to D of A of y dy. And so you may need to calculate the volume with a definition with respect to y. It depends on the problem. Right? And so for a disk, the area of a disk, right, the area of a disk would be pi times r squared. The area of a washer would be pi times capital R squared minus pi times little r squared, where the washer is kind of the region between two circles. Right? And little r is the radius of the smaller circle, and capital R is the radius of the larger circle. So this is a brief overview of 7.2. We calculate volumes with one of these two definite integrals, and we can use the disk method or the washer method to do that. And so we'll do examples, and it's really the best way to review this is through examples. All right, so that's 7.2. All right. In 7.3, we talk about volumes by cylindrical shells. Okay, so in 7.3, we now add another method to calculating volumes, and that's a method by cylindrical shells. And so the volume is equal to the definite integral from a to b of 2 pi x f of x dx. Okay, so this is a brief overview of 7.3. where 0 is less than or equal to A, strictly less than B. Okay, and so this is the cylindrical shell method. Now instead of x, right? Well, first the differential could be with respect to y also, so you could have 2 pi y f of y dy. All right, where c is less than or equal to y, strictly less than d. Okay, so you could maybe use a differential with respect to y instead of with respect to x. This is called this is using this cylindrical shell method. Okay, so the cylindrical shell method is calculating the volume using one of these two definite integrals, except instead, this is really the radius of the cylindrical shell. The cylindrical shell looks like this, and it has a kind of a thickness here. And so really the volume of a cylindrical shell is 2 pi r h delta x. And so when I write these two equations, it's for when we have cylindrical shells whose radius is x, and the height of the cylindrical shell is f of x, okay? And here it's when the radius is y, and when the height of the cylindrical shell is f of y. But that does not always have to be the case. These are the easier cylindrical shell problem method formulas. Instead of x here, you might have a radius that's different than x. And instead of f of x here, you may have, instead of the value of the function, you might have a difference of two functions or something else, okay? And so these are the formulas just for the simplest versions of using the cylindrical shell method. If you're dealing with a more difficult cylindrical shell method problem, then what's different is that instead of this or this, you might have a different radius. And instead of this or this, you may have a different height. All right? And so in each problem, you need to know what your radius is of your cylindrical shell and the height is. And you put the radius of the cylindrical shell here and the height of the cylindrical shell there. And in this case, you put the radius of the cylindrical shell here and the height of the cylindrical shell there. Okay, so this is the height of the cylindrical shell. And this is the radius of the circle of the cylindrical shell. Okay? Same thing here. This is the radius and that's the height. Alright, so this is the cylindrical shell method. And so when we do examples, we'll see some of the cylindrical shell method. And so that's 7.3. It's a summary of 7.3. Okay, the next section is 7.4, which is about arc length, and it starts on page 392. Okay, so the arc length formula, it says on the bottom of page 393, if f prime is continuous on the interval AB, then the length of the curve y equals f from A to B is capital L, which equals the definite interval from A to B of the square root of 1 plus f prime of x squared dx. Okay, this is if f prime is continuous on the interval a comma b, and the length of y equals f from a to b is this. So this is the arc length formula. So this is how you compute the arc length. Okay, so another way to write it is using Leibniz notation. And so this is the same equation and just written with different notation. Okay? This is Leibniz notation. Instead of f prime of x, writing dy dx is Leibniz notation. And so this is with respect to x. You could also use the arc length formula for integrals with respect to y, and that would be the definite integral from c to d of the square root of 1 plus dx dy squared dy. Alright? And so you could either have it like this or like that. And I'm using Leibniz notation to express that one also. I find Leibniz notation better for this. I think it is. Okay, and so then there's also the arc length function. And the arc length function is s of x equals the definite integral from a to x of the square root of 1 plus dy dt squared dt. And so you need to be able to compute the arc length function also. That's called the arc length function. All right, so in 7.4, you need to be able to use the arc length formula, either as an integral with respect to x or definitive with respect to y. And you need to be able to compute the arc length function, find the arc length function. All right, so that's a brief summary of 7.6. And then after 7.6, we go to 7.7. And so for 7.7, it starts on page 418. Okay, so page 418. Okay, so on page 418, we talked about 7.7, which is differential equations. Okay, so a differential equation is an equation that contains an unknown function and one or more of its derivatives. Right, so it contains a function and one or more of its derivatives. So that's a differential equation because it's an equation that involves a function y and one or more of its derivatives, in this case y prime. Y double prime plus 2y prime plus y equals 0. That's another example of a differential equation because it's an equation that involves a function y and one or more of its derivatives, in this case y prime and y double prime. All right, a solution of a differential equation is just a function, let's say y equals f of x, that satisfies that differential equation. And what that means is you could plug in y and its corresponding derivatives into the equation, and the equation would be true. Right? So in this case, if we were given a y equals f of x, and we found y prime and y double prime, and we plugged them into this equation, then that expression would equal 0. That means this y would satisfy that differential equation. Okay? Solutions of a differential equation are functions. Right? As we can see, that's a solution. If the function and its derivatives, when plugged into the differential equation, satisfy it. Okay, the order of a differential equation is like the highest power derivative in the differential equation of the function. So here the order of this is 2 and the order of that is 1. Okay? Alright, so that's the definition of a differential equation. Also afterwards is the idea of a separable differential equation. Okay, and so let's say I give an example like dy dx is equal to x squared e to negative y. This would be an example of a separable differential equation because we were able to say that dy dx is equal to a function of x times a function of y. And we could have also solved this to say that this implies that e to the y dy is equal to x squared dx. We were able to move everything with y on one side and everything with x on the other. This is an example of a separable differential equation. Right? And so we learned in 7.7 to solve separable differential equations. Right? So you need to know how to be able to solve separable differential equations. Right? Also, differential equations often, another type of differential equation problem we solved was an initial value problem, where we're given an initial value. We're given some initial value condition, and we need to find not a general solution of the differential equation, but a particular solution that satisfies our initial condition. That's called an initial value problem. So again, if you're given a differential equation and some initial condition, like y of 0 is equal to 5, right? When x is 0, y is 5. Then the solution of that, what's in the box here, would not just be the general solution, would not be the general solution of the differential equation, or finding all the solutions to differential equation. It would be finding the particular solution of the differential equation that satisfies the given condition. In this case, y is 0 equals 5. Okay? That's an initial value problem in differential equations. Okay? So you need to be able to solve an initial value problem and solve a separable differential equation. Right? You need to know the order of a differential equation. You need to know the definition of a differential equation. Those are some of the things you need to know in 7.7. Okay? And so that's a summary of 7.7. All right? So we've gone over the sections. So now let's spend some time doing a few review problems. Okay? All right, so go to page 428 in the textbook, 428. Okay, that's the review exercises at the end of chapter 7. All right, so let's start with number 1. So this is number 1 on page 428, and we're looking at the exercises at the end of the review, in the review section of chapter 7. Okay. Okay. So for number 1, we're given y equals x squared, and y equals 4x minus x squared. Okay, so we want to find the area of the region bounded by those given curves. And we're going to find the area of the region bounded by those curves. So y equals x squared looks like this. Okay, so you need to be able to draw y equals x squared. And y equals 4x minus x squared. So what is the graph of that? Well, if I were to think of this as the negative of x squared minus 4x, well, I would think of x squared. If you think of x minus 2 in parentheses squared, and the reason why I did that was because x squared is x squared, and half of negative 4 is negative 2. And so if you take x minus 2 and you square it, you get x squared minus 4x plus 4. All right? And so this function is the negative of x squared minus 4x. But it's also equal to the negative of x squared minus 4x, and then add the 4 there in parentheses. But now I subtracted 4, and so I need to add 4 here, and so it's still equal. And so if I took this and I added a 4 here, I'd really be subtracting 4 because the negative sign distributes. And so I'm subtracting 4 here with this plus 4, and then I add 4 at the end, and then negates it. Okay? And so now, because I know this equation, the original function y equals 4x minus x squared is equal to the negative of x minus 2 squared plus 4. All right? The negative of x minus 2 squared plus 4. All right, so now we can graph that. We're just translating y equals x squared. We're just moving it. So we have the graph. We want the graph of y equals negative of x minus 2 squared plus 4. All that is if you take the graph of y equals x squared, you move it to the right 2 units, then you flip it with the negative sign, and then you move it up 4 spaces. So you move it to the right 2, you flip it, you reflect it about the x-axis, and then you move it up 4. Right 2, reflect it with the y-axis, up 4. So we're going to move this graph to the right 2 spaces. We're going to reflect it like this over the x-axis. So now it's going to look like this. And then we're going to move it up 4. And so the graph we get is this graph. So it goes to the origin. You plug in x equals 0, you get negative 4 plus 4 is 0. And then also, x equals 4, that's also, so this is the point 4 comma 0, and this is the origin. So this graph starts up here, and okay, it just looks like that. Okay, so this is the graph of y equals the negative of x minus 2 squared plus 4, which is the same as 4x minus x squared. Right? So we now have the graph of this graph, and we have the graph of the y equals x squared. And so what we want is the area of the region between those two functions. Okay? So if we look at an approximating rectangle here, it would look like that. So that tells us that the top function is this function. Right? The top of the rectangle is this function. This is the top function. This is the bottom part of the rectangle is on this curve. And so this is the bottom function. Okay, so I'm just labeling the functions as top function and bottom function. So that means the area is equal to the definite integral from 0, because the width of the rectangle is a delta x. So it's from x equals 0 to x equals, this x coordinate is 2. Yeah, when x is 2, then you get y equals 4. Okay, so that's 2 comma 4, but we want the x value here. So we have x equals 0, x equals 2. So it ranges from 0 to 2. Oh, wait, sorry. That's the intersection points. I mean, that's the topmost of the point of the problem. We want the intersection points of the two graphs. And so they both cross the origin. Well, what's this point? So we're going to find this point. So to find this point, I'm going to erase this part. This is the part where help me draw the graph. I don't need that now. Okay. Okay. So now we're going to set the two functions equal to each other. y1 equals y2. That means x squared is equal to 4x minus x squared. That means you have 2x squared minus 4x is equal to 0. That means 2x times x minus 2 equals 0. So either x equals 2, x equals 0, or x equals 2. Alright? Okay, so now drawing this graph better, so it turns out that this y equals x squared will crosses that point, right? Crosses that point. Okay, that's the intersection point of the two graphs. Let me draw this graph better now. Now that I see how the graph is split. That's the region between the two curves, and it crosses the point 2, 4. This is an approximating rectangle. Okay, delta x is there. So it is from 0 to 2. Okay, and so we take the top function, which is 4x minus x squared. That's the y value of that graph, minus the y value of this graph, the bottom function, which is equal to y, x squared. So it's minus x squared dx. So it's that definite integral, and so you calculate it. And so calculating that definite integral, we get, this is the top function. I'm just going to write that here so I can keep writing equals. So this is equal to an antiderivative of that. But actually first, I'm going to just combine like terms. So you get 4x minus 2x squared as the integrand function. So this is 2x squared minus 2/3 x cubed. And you evaluate it from 0 to 2. And so that equals, so if you plug in a 2, you get 8 minus 16/3 minus 0. And so if you subtract that, you get 8/3. And that's the answer. So the area is 8/3. Alright? 8 is 24/3, so 24/3 minus 16/3 is 8/3. That's the area of that region between the two curves. Okay, so again, this is the top curve of the top function here, because it's the top of the region, and it stays the top of the region the entire time. So this is the top function. And the bottom curve is here, right, throughout, and the bottom function is y equals x squared. So top function minus bottom function. And the x values range because the width of the approximating rectangle is a change in x values. So it's a difference with respect to x, and it ranges from 0, the shade region ranges from 0 to the left to 2 to the right. All right, so that's number 1. Okay. Yeah. Okay, so let's do number 2. So for number 2, it says still find the area of the region bounded by the given curve. So y equals 1 over x, y equals x squared, y equals 0, and x equals e. Okay, so those are our 4 functions that we're going to graph. And so x-axis, y-axis. So this is y equals 1 over x. That's the curve of y equals 1 over x. And then there's the graph of y equals x squared. Y equals 1 over x, y equals x squared. Y equals 0. And x equals e. That's e. Okay, so first off, these two graphs intersect at the point 1, 1. When x is 1, y is 1 for both functions, right? Okay, they also no, that's just the origin. Okay, so that intersects there, and then x equals e. Let's say x equals e is here. So the right of x equals 1. And y equals 0. Okay, so y equals 0 is, y equals 0 is this. Okay. So this graph actually does not cross does not touch the x-axis, but because of the vertical line x equals e, we stop at e. What we want is the region bounded by y equals x squared, y equals 1 over x, x equals e, and y equals 0. So you get this region here. That's the region bounded by those 4 curves. And it's bounded by x equals here, e, by this little tiny vertical line there. That's the contribution of that one graph, x equals e. Okay, so to evaluate this integral, let's think about what stays the same throughout. So if I drew an approximating rectangle, a horizontal one, instead of a vertical one, your first thought is a vertical one. But if you do a horizontal one, then the right function is always this one. And the right function is always y equals 1 over x. This is the right function, right? It's the right function, the right side of the approximate rectangle. The left side of the approximate rectangle is on y equals x squared. So that's the left function. And so the area, capital A, of that shaded region is the definite integral. This is a delta y, the width, right? It's vertical, so the length is a change in y values. And so we're integrating with respect to y. And so the y's range from 0 to 1. And so it's the right function, which is, but now so this is a x, this is a difference of x values, right? But each x value, it has a corresponding, so x here equals 1 over y. And so the rightmost x value is equal to 1 over y, minus the left x value, which is equal to the square root of y. So that's 1 over y minus the square root of y, dy. Okay, so now we integrate this. So this is ln of y minus, this is the same as y to the 1/2. And so an antiderivative of that is 2/3 y to 3/2. Okay, we take that and we evaluate it from 0 to 1. So, oh, sorry, wait, this won't work. Okay, so the reason why this won't work is because the horizontal rectangles, the 1 over x function is to the right until this point, and then there's a vertical part. So the horizontal rectangle actually will stop it here. Okay. Now I could find this point on the curve, the y value, and continue with this method, which I'm thinking of maybe doing. Because if x is e, the coordinates of this point is e comma y value on the graph of x equals 1 over y, or y equals 1 over x. So y is 1 over e. That's 1 over e. And so instead of erasing all this, I'm going to continue with this way of doing it, which is fine. And so what I'm going to do is I want you to see the graph. Again, I could make this work, but I don't want to because I think it's more. I think this is the wrong way to go back. Let me go back. Let me backtrack. Let me backtrack instead of using a horizontal rectangle, which I thought would be faster. Let's use a vertical rectangle, which will, 2 vertical rectangles. Because this region here, there's a top function here and a different top function here. We have to separate this region into 2 subregions, where we need to find the area of this, and then separately find the area of that, and then add the 2 areas. Okay, so the total area, capital A, is equal to A1 plus A2. And that's equal to, A1 is equal to the definite integral from, we're going to have vertical rectangles here with the delta x thickness. So the definite integral from 0 to 1 of something, plus the definite integral from x equals 1 to x equals e of something else. Okay, so we're splitting it up into x equals 0 to 1, and then from 1 to e, to find A1 and A2 respectively. And so now what's the height? It's x squared minus, it's just x squared. And so this is, so now it's definite from 0 to 1 of x squared dx. All right, and now this one is, this is 1 over, this is 1 over x here. Okay, it's not left or right function, okay. So now it's 1 over x dx here. Okay, so this is equal to x cubed over 3 evaluated from 0 to 1 plus ln x evaluated from 1 to e. So this is equal to 1 cubed over 3 minus 0 cubed over 3 plus ln e minus ln 1. And so ln of e is 1. This is 1, and that's 0. This is 1 minus 0. This is 1/3 minus 0. 1/3 plus 1 is 4/3. So that equals 4/3. The answer is 4/3. And so that's number 2. So here we have to split up into 2 subregions and use vertical rectangles. I tried to use one region, but because of this little vertical part here, you can't do it in one shot, and so this way is actually the easier way. So you do sometimes need to separate the region into 2 or more subregions and find the areas separately and then add them up, like in this problem. Okay, so that was a good problem to go over. So that's number 2. These are examples of finding the area, finding areas from 7.1. Okay, another problem, let's say, is number 5. All right, so for number 5, so we're given the curve y equals 2x, y equals x squared. And we want to find the region bounded by those 2 curves, and we want to rotate that region about the x-axis and find the volume of the resulting solid. Okay, so you have the textbook at home. So here's the x-axis and y-axis. We have y equals x squared. So y equals x squared. And then we have y equals 2x. So we have y equals 2x. Y equals x squared and y equals 2x. And so let's take the origin here. And then this point, and so finding intersection point at this point is finding where the 2 y values are equal, which is when x squared equals 2x. That's x squared minus 2x is 0. X times x minus 2 is 0. So either x equals 0 or x equals 2. Okay, so when x equals 2, y is equal to 4 in both functions. So the other intersection point other than the origin is at the point 2, 4. And so this is the region bounded by those 2 curves. We're going to rotate it about the x-axis. Okay, so you rotate this about the x-axis, and you get that mirror image. And now it's actually being rotated, not just finding the mirror image, and so everything wraps around the x-axis, right? So here we're rotating about the x-axis, that shaded region. We're rotating it about the x-axis. All right, so we're going to find the area of this, and so we can use whatever method we want. Let's use the cylindrical shell method. So here's one vertical line. So you can think of, a horizontal line. You can think of the horizontal lines here sweeping across the shaded region. and then each separate one would rotate around the x-axis, and each rotation would give you a three-dimensional cylindrical shell with infinitesimally small thickness. So here's an example of a cylindrical shell. Okay, so the volume is equal to the definite integral, and now the thickness of it is a change in y values. And so we're going to integrate with respect to y. The y value starts at 0 of the shape of the original region and goes to y equals 0 to y equals 4. And so the definite integral is from 0 to 4, and then it's 2 pi. The radius of the cylinder is the length of that. Well, this is the x, y coordinate on a curve, right? That's the y coordinate of this point. That's the radius. So it's 2 pi y times the height of the function, the height of the cylindrical shell. The height of the cylindrical shell is the difference in y value, the difference of x values of two functions. And so this is the right function, and this is the left function. The right function is here, y equals x squared. The left one is y equals 2x. So these are difference of x values, and you solve each x for y. You get x equals y over 2 here. So the left function is x equals y over 2, and the right function is x equals the square root of y, or y to the 1/2. Okay. So the right function is y to the 1/2. So it's the right function minus the left function, which is y over 2. Okay, so the change in x values is it's this x value minus that x value. This x value is equal to y to the 1/2 minus the left x value, which is equal to y over 2. So it's y to the 1/2 minus y over 2. And that's dy. So you just calculate this definite integral, and then that's the answer. So this is 2 pi times the definite integral from 0 to 4. Y times that, which is y to the 3/2 minus 1/2 y squared dy. Right? So now this is equal to 2 pi times the antiderivative of that, which is 2/5 y to the 5/2 minus 1/6 y cubed, evaluated from 0 to 4. And so that's equal to 2 pi times, if you plug in 4, you get something. If you plug in 0, you get nothing. So you just, it's this plugging in 4 minus 0. So when you plug in 4, you get the square root of 4, which is 2. 2 to the 5th power is 32. 32 times 2/5. It's 64 over 5 minus, plugging in a 4 here. 4 cubed is 64 over 6. That's 64 over 6. And so the answer is 2 pi times 64 over 5 minus 64 over 6. And you can simplify that if you want a little bit. I could write this one fraction and multiply it. We can stop there. Okay? 64 over 5 is a little bit larger than 64 over 6, so this is constant. We're good. Okay, small denominator means bigger fraction with the same numerator. Okay, so that's number 5. We use cylindrical shells for this one. So this is practice for the cylindrical shells section. Okay, let's do number 7. So for number 7, you have x equals 0. X equals 9 minus y squared. And we're going to, so the region bounded by x equals 0 and x equals 9 minus y squared. And we're going to rotate that region, bounded region, about x equals -1. All right, so let's do that. So first let's graph those two. So x equals 0 is the y-axis. X equals 9 minus y squared. So I see better when it's y equals something. So I'm going to think of y equals 9 minus x squared. I'm going to think of that graph, and then I'm going to reflect it about y equals x. and that will switch the x and y values, right? So I want this graph. If I graph this and I reflect it about y equals x, then I'll get the graph of x and y being switched. So y equals 9 minus x squared is, you have negative x squared plus 9. So this is the graph of y equals 9 minus x squared. And then reflect that about the line y equals x. Okay, so what happens when you reflect that? So this point in the original graph is x equals 0, y equals 9. And so this point will be 9, comma 0. And so it was going down, now it's going to go to the left. Okay? And so if you're good at rotating here, when you rotate this about y equals x, it's going to go that way. Okay? And so now the new graph will look like that. Okay? I'm not worried about where it crosses the other graph because it actually, it may not have to cross there. Let's just erase the other graph here. We don't need y equals x either now, because we're only using it to draw this graph, which is here now. All right, and we'll erase that point too. So where does this graph cross the y-axis? When x is 0, y is plus or minus 3. This is 0, comma 3, and this is 0, comma negative 3. Okay, forgetting about the other graph I drew, that was just to get perspective on how to draw this one. So this is y equals, this is x equals 9 minus y squared. This is x equals 9 minus y squared. Okay, and x equals 0, again, is the y-axis. And so the region bounded by those two curves is this region here. I'm going to rotate this about the line x equals negative 1. That's the line x equals negative 1. And so when you rotate that, you get this point, and you get this point. Okay, and so that's the mirror image of that shade region about the line x equals negative 1. And so we're just rotating it now. So I'm going to get rid of this part of the other graph and this part because we don't need it. Okay, we have that part that we wanted. Now I'm going to rotate this around the line x equals negative 1. And now you get that. Okay, so now that's your three-dimensional region. And so we're going to find the volume using washers. And so also this is being rotated in here. And so an example of a washer would be this thing here. That would be an example of a washer. Okay, so if you think of the other thing I'm shading, I'm also shading in this washer. All right, so now that's an example of a washer with a very small thickness. And that thickness is a change, right? If you think of the height of this washer, it's a change in y values. So that tells you that we're calculating the volume as a definite rule with respect to y. Because the thickness of the washer is a change in y values. Okay, there's a delta y here for the thickness of it. Okay, so the volume of a washer, remember the volume of a washer is pi times capital R squared minus pi times little r squared. It's just taking the area of a larger circle and removing from it the area of a smaller circle and centered at the same place, right? We're just taking the area of the larger circle and we're subtracting the area of the small circle. So little r is the radius of the small circle, capital R is the radius of the larger one. All right, so here, what is little r? Right, well, little r is this, right? That's little r. Little r is the length of this. It's starting at x equals negative 1, and then you just go to x equals 0. On the y-axis, the length of little r is 1. Little radius is always 1. Okay, no matter where you are here, the little radius is 1. If I drew another washer over here, right, this washer, this little r is still 1. It's that same distance. Little r is 1 throughout, which is it's supposed to be. Now capital R, I'm now going to extend this. Capital R is the length of this, or the length of that whole thing, okay? Little r equals 1 is only this part of it. That's little r equals 1. Now this whole thing is the larger radius. And so the x distance of a point on this curve, right? This is a point x comma y on the curve x equals 9 minus y squared. The x distance of the point is that. And that length is 1. And so the larger radius is 1 plus the x coordinate of this graph, which is 9 minus x squared. So capital R is equal to the x coordinate of the horizontal distance of the point, the x coordinate of the point, which equals 9 minus y squared, plus 1. And so capital R is 9 minus y squared plus 1, which is 10 minus y squared. So capital R, the larger radius, is 10 minus y squared, and the little radius is 1. And so the washer, the washer is pi times the larger radius, 10 minus y squared, minus pi times the radius of minus the smaller radius squared, which is 1 squared. And so that's our integrand. And we're integrating from the smaller y value, which is -3, going from the original shade region here is from y equals -3 to y equals 3. And so our volume is the depth interval from -3 to 3 of pi times 10 minus y squared minus pi times 1 squared dy. So when we calculate this depth integral, we found the volume of our three-dimensional solid of revolution. And so this is equal to, the pi is going to just be moved out of the depth integral. And then we have, I guess I'll write it, depth integral from -3 to 3 of 10 minus y squared. That's 100 minus 20y squared plus y to the 4th. That's 10 minus y squared. And then minus pi times 1 squared. It's minus, but the pi is out this. This is minus 1. dy. Okay, it's minus pi times 1 squared, but I factor the pi out over here. And so that's equal to, so this is equal to this. That's equal to pi times, now I'm going to just combine like terms here, which is not much work. This is y to the 4th minus 20y squared. And then plus 100 minus 1, which is plus 99 dy. All right. Very good. And so now that's equal to pi times an antiderivative of the integrand function, which is y to the 5th over 5 minus 20 y cubed plus 99y, evaluated from -3 to 3. Okay, so this is using the evaluation theorem. Okay, so an antiderivative of y to the 4th is y to the 5th over 5, an antiderivative of 20y squared is 20 over 3y cubed, and antiderivative of 99 is 99. Okay, so you evaluate from -3 to 3. And so that's equal to pi times, plugging in 3, doing the calculation, you get 243 over 5 minus 3 cubed over 3 is 3 squared, that's 9 times 20, which is 180, minus 180, plus 99 times 3, which is 297, is that, minus, now plug in a negative here. And so if you plug in a -3 everywhere, you're going to get the negative of that. Okay? So if you plug in a 3 here, you've got a term. And because it's y to the 5th, y cubed, and y, if you plug in -3 instead, you're going to get the negative of it. But you're subtracting the negative of it, which means you're adding another one of these guys. So there's 2 of these. So in any case, you calculate this. Okay, there's 2 of that. And so let me just do the calculation. This is 2 pi times that, which is 117 plus 243 over 5, which is the same as 48.6. Okay, and so this is 165.6. Okay, so this is 168.6 times 2 pi, and that's the same as 337.2 pi. 320, 336, and then good. So 337.2 pi, and that's the final answer. That's the that's the volume of that three-dimensional object. Okay, so you have to follow the arrows here, running out of space here. This is equal to this, which equals this, which equals this, which equals this. Okay, and this is using washers again, okay? To find the volume. That's number 7. Okay, so let's do another problem. So for number, let's go to 25. So we did some volume problems, and we did area and volume problems. So for 25, is find the length of the curve. So the curve is y equals 1/6 times x squared plus 4 to the 3/2. Where 0 is less or equal to x, less or equal to 3. Okay, so we want to find the length of the curve for this problem. So the arc length formula is capital L is equal to definite integral from a to b of the square root of 1 plus dy dx squared dx. Okay, so what we want to do is find dy dx and plug it in here, and then calculate find a way to calculate the definite integral. So dy dx for that y is its derivative. So you find the derivative of 1/6 times 3/2 is 1/4 times x squared plus 4 to the 1/2 times 2x, the derivative of x squared plus 4. So dy dx is 1/4 times x squared plus 4 to 1/2 times 2x. That's the same as 1/4 times 2 is 1/2. So you get 1/2 x times x squared plus 4 to the 1/2. So dy dx is equal to that. Okay, so dy dx squared is equal to the square of that, which is 1/4 x squared times x squared plus 4. Because you square this to the 1/2 squared is that to the first. Okay. So that's dy dx squared. So 1 plus dy dx squared is equal to 1 plus that. 1 plus 1/4 x squared times x squared plus 4. And that's equal to multiplying out 1 plus 1/4 x to the 4th plus x squared. Okay, rearranging the terms, this is equal to 1/4 x to the 4th plus x squared plus 1. So we have 1 plus dy dx squared is equal to 1/4 x to the 4th plus x squared plus 1. That's what's in the square root here, right? So here's a trick. Take this term and this term, the two terms with x in it. What's the square root of 1/4 x squared? It's 1/2 I mean, what's the square root of 1/4 x to the 4th? It's 1/2 x squared. What's the square root of x squared? The positive square root of it. It's plus x. Take that and square it and see what you get. Taking that squared, you get 1/4 1/4 x to the 4th plus 1/2 x cubed plus 1/2 x cubed, which is just x plus x cubed plus x squared. It didn't work. Okay, so let me just check my math here. 2y dx is equal to 1/4 x squared plus 4 to 1/2 times 2x, which is 1/2 x times x squared plus 4 to 1/2. That squared is 1/4 x squared times that. Okay. So this didn't work. I wanted it to. So instead, let's go up to this point. Okay. This is equal to this. Okay, so we're going to plug this in. This is differential from 0 to 3 of the square root of 1 plus dy dx squared, which is 1 plus 1/4 x to the 4th plus x squared dx. Okay. So if I could express this as something squared, that would do it. So figure 1/2 x squared is one term. 1/2 x squared plus 1 squared. If you square that, you get 1/4 x to the 4th plus 1/2 x squared plus 1/2 x squared, which is plus x squared and then plus 1. That's it. 1/2 x squared plus 1 squared is 1/4 x to the 4th plus x squared plus 1. And so what's encircled in here can be replaced with 1/2 x squared plus 1 in parentheses squared. So I'm going to do that. Okay, so this is now equal to 1/2 x squared plus 1 squared. 1/2 x squared plus 1 in parentheses squared. That's that expression. This is differential from 0 to 3 of that dx. Well, you square root something squared and you get back what you started. So this is differential from 0 to 3 of 1/2 x squared plus 1 dx. And so find an antiderivative of the integrand, and you get 1/6 x cubed plus x, evaluate from 0 to 3. So you get 27 over 6 plus 3. And so that's 45 over 6. So that's 7.5. That's 7.5. All right, so the final answer is that the length of that curve is 7.5. So what I did was I took this expression, which is 1 plus dy dx squared, and expressed as 1/2 x squared plus 1 in parentheses squared. And the square root and the square cancel, and you're left with that. And you integrate it, and you find the differential, you calculate it, and you get 7.5. Right? So that's number 25. So that's finding the length of a curve using the arc length formula. That's 25. So let's make sure we do a little bit about differential equations. 7.7. Let's do a differential equation problem. All right, so let's do number 43. Okay, so 43 on page 430. Same review problems, okay? Solve the differential equation. So you have 2y e to the y squared y prime is equal to 2x plus 3 root x. All right? So if you think of this as a separable differential equation, then it ends up being not too bad, okay? So I'm going to write this in Leibniz notation. So I suggest you use Leibniz notation. It might make things easier. Okay, so we have 2y times e to the y squared times dy dx equals 2x plus 3 root y, 3 root x. I'm going to move the dx to the right side. So this is 2y e to the y squared dy is equal to 2x plus 3 times x to the 1/2, which is the square root of x, dx. So this is a separable differential equation. I'm going to integrate both sides. Okay, the right side, the integral is x squared plus 2x to the 3/2. This is finding the antiderivative of that. And then there would be a plus c here. The plus c would be for both sides. This side is the integral of this. We'll let u equal y squared. What's in that? Then that integral, the integral of 2y e to the y squared dy is equal to, well, u is y squared, du is 2y dy. So this is equal to the integral of e to the u, 2y dy is du. And so this integral is the integral of e to the u du, which is e to the u plus a constant, right? Plus d, I guess I'll call it, just for here. But then when we plug in the e to the, this is e to the u, e to the u is u is y squared. So this is e to the y squared plus a constant. That's what this thing is. This is e to the y squared plus a constant. So here, this is e to the y squared, and then the plus c is the difference of the constants you add to both sides. So it's the constant you add to this side minus the constant you add to that side. That's this plus c here. So e to the y squared is equal to x squared plus 2x and 3/2 plus c. That's solving for y implicitly in terms of x. And that's the general solution of this differential equation, right? So you use u substitution to solve the left side, and the right side you can just use the evaluation theorem to get the right side. Right? You use the evaluation theorem here, also the left side. Okay, and so that is a solution of a differential equation. Continue. Okay, so let's do number 45. 45 is solve the initial value problem. So 45 is dr dt plus 2tr is equal to r. And r of 0 is equal to 5. All right, so let's solve this initial value problem. First we'll find the general solution, and then find the value of the constant that satisfies this equation. So first find the general solution. It'll use a constant and find the value of that constant that satisfies this equation. Okay, so dr dt is equal to r minus 2tr. That's equal to r times 1 minus 2t, factoring out the r. And so the dr dt is equal to r times 1 minus t. Moving the r to the left side and the dt to the right side, you get 1 over r dr is equal to 1 minus 2t dt. You integrate both sides, and you get ln r you get ln r on the left side and the right side, you get t minus t squared plus a constant c. And so now that's ln r is equal to that. This is solving for r implicitly in terms of t. You could solve for r explicitly in terms of t. You take e of both sides. So you took e to the ln r equals e to the t minus t squared plus a constant. You get r is equal to e to the t minus t squared plus a constant. Actually, I'm going to use plus d for the constant. And here's why. So this is equal to e to the d times e to the t minus t squared. And this is equal to c times e to the t minus t squared, where c is e to the d. This is constant though. So solving for r of t is equal to c times e to the t minus t squared. That's solving for r explicitly in terms of t. Okay, r of 0 is 5. So plug in 0 for t, and you get c e to the 0 minus 0 squared. That's e to the 0, which is 1. This is equal to c. R of 0 is 5. So you need c equal to 5 in this equation. So the final solution is r of t is equal to 5 e to the t minus t squared. That's r of t. All right. Okay, so that's number 45. Okay, so now we've solved the differential equation in number 43, and we solved an initial value problem in number 45. Okay, and here we had a separable differential equation. So we cover those three things in those two examples. All right, so we did a whole bunch of problems there. Let's do one more. Number 6. For number 6, we want to find the volume of the solid obtained by rotating the region bounded by the given curves about given axis, specified axis. X equals 1 plus y squared. Y equals x minus 3. About the y-axis. Okay, so x equals 1 plus y squared. X equals y squared would look like this, and you move it to the right one. So x equals 1 plus y squared looks like that. So again, x equals y squared looks like that. And you just move it to the right one, because that 1 is moving it to the right one because it's x equals. So you move it to the right one, and you get that. For this point is 1 comma 0. When x is 1, y is 0. Okay, so that's x equals 1 plus y squared, and then there's y equals x minus 3. That's y equals x translated down by 3 units, and so that's y equals x minus 3. Okay, so now let's look at the intersection points of these two curves. It's here and it's here. So let's say y1 equals y2. That means that one function, x minus 3, is equals the other one. One is x equals, one is y equals. So instead of we're going to rotate it. So we're going to, well, I'm going to do a picture. We're going to rotate about the y-axis. So if we rotate it about the y-axis, we're going to get something kind of like that. And then we're going to rotate it. Okay, and so when we rotate it, to find the total volume, we can use cylindrical shells. So the cylindrical shells will look like that. This is the shaded region here, region bounded by the two curves. And so you have a cylindrical shell that looks like this. Get rid of that. Okay, and so the thickness is delta x. And so the volume is going to be a definite with respect to x. And so when we talk about the height of the function, we're going to be talking about y. And so we want to solve in terms, what we want y equals. All right, so for this graph, we want y equals. So x equals 1 plus y squared. It's x minus 1 equals y squared. Y is equal to the square root of x minus 1. So this is, or y equals the square root of x minus 1. Okay, so this is this function, and then it's that function. Y equals for both. So we want to know what values are the two functions the same. So, so I'm seeing it. So, so x minus 3 equals the square root of x minus 1. So you square both sides and you get x minus 3 squared is equal to x minus 1. That's x squared minus 6x plus 9 equals x minus 1. X squared minus 7x plus 10 is equal to 0. That's x minus 5 times x minus 2 equals 0. And so that means x either equals 2 or x equals 5. So this is finding the intersection points of the two graphs. Okay, so we see the intersection points when x equals 2 or x equals 5. And so when x equals 2, the corresponding point is y equals 1. When x is 2, when x is 2, y is negative 1. Y is negative 1. Okay. Okay, and then when x is 5, 5 minus 3 is 2. 5 comma 2. Right, so if our definite integral, capital V, is with respect to x, so this is with respect to x, and so the x values range from 2 to 5. From 2 to 5. It's different from 2 to 5 of the top function, which is the square root of x minus 1, or x minus 1 to the 1/2, minus the bottom function, which is x minus 3. Okay, so it's the top function minus, it's washers, sorry. That's the height. But okay, so the washer means that the radius of we're using cylindrical shells. The radius is just the x coordinate. And it's with respect to x. We're good. This is 2 pi x times the height. 2 pi x times the height. 2 pi x is the circumference of the circle. The height is now the difference of y values. And the difference of y values is now this x minus 1 to the 1/2, the top function, minus the bottom function. This is the top function, this is the bottom function. And minus x minus 3. dx. And so now I'm looking at this differential, I'm wondering how I'm going to calculate it. Okay, I can get the value of it. There might be an easier way than the way I did this problem. Let's keep going. Okay, so now, so we have this definite interval, okay, with all this work. And so actually I'm seeing it's going to take a little bit of calculations to do this, so I have to erase all this to calculate this definite interval. So let's do that. So we get so far that this definite interval is the volume using cylindrical shells. And so now I'm going to find that definite interval. Okay, so I'm going to find that definite integral. It's going to take a little more work than I expected, so I'm going to have to erase all this to do it. So I'm going to use U substitution, and I'm going to use a weird U substitution. Let's do it. Okay, so this is definitely from 2 to 5 of that. So the volume is 2 pi times the definite integral from 0 from 2 to 5 of x. So 2 pi times what I'm going to put after this. So I'm factoring 2 pi out of everything I'm doing. And that's the definite from 2 to 5 of x times x minus 1 to the 1/2. And now I'm going to say dx, and I'm going to subtract, I'm going to separate this into two terms, minus x times x minus 3 dx, which that will be easy to calculate. It's this one that is a little weird, but that one will be fine. Okay, so then I'm going to let u equal x minus 1 to the 1/2. I'm going to let u equal x minus 1 to the 1/2. du is equal to 1/2 times x minus 1. Maybe I could still get this to work. Okay, so then, so definitely from 2 to 5 of x times x minus 1 to the 1/2 dx. This is what I want to compute. I'm going to write this as definite from 2 to 5 of x times the fraction x minus 1 to the 1/2 over x minus 1 to the first power. I need a 1/2 here. So I'm going to add a 1/2 here and a 2 here. And we have our dx there already. And so our 1/2 x times x minus 1 to the negative 1/2 is there. That's du. And so this is equal to 2 times the integral. Now u is that. U squared is x minus 1. So u squared is x minus 1. That will go there. U squared plus 1 is x. So this is the 2 times the definite integral. X I'm going to substitute with u squared plus 1. And x minus 1 I'm going to substitute with u squared. And then the rest of it is du. And when x is 2, I get u is 1. When x is 5, I get u is 2. That's good. So then this is equal to 2 times the definite integral from, so this is up here. So now this is the 2 times the definite integral from 1 to 2. U squared plus 1 times u squared, that's u to the 4th plus u squared du. This is equal to 2 times u to the 5th over 5 plus u cubed over 3 evaluated from 1 to 2. Okay, and this is equal to 2 times, plugging in 2 here, 2 to the 5th over 5 plus 2 cubed over 3 minus plugging in 1, and so you get 32 over 5 plus 8/3 minus plugging in a 1, 1/5 plus 1/3. Okay, and so then that's equal to 2 times, so this is 31 over 5. This minus this minus this is 31 over 5. 8/3 minus 1/3 is 7/3. This is plus 7/3. And so when you combine that, you make 15 the common denominator, and you get 2 times 93 plus 35 over 15. Okay, so that's 128. 93 plus 35 is 128 times 2, which is 256 over 15. All right? That's the simplest. That's in fractions reduced. So this definite integral is equal to 256 over 15. All right? So I'll leave that on board for a moment so you can see it. That definite integral is equal to 256 over 15. This one. All right? And so I'm going to plug that in here. So this definite integral there is 256 over 15. Okay, so now I'm going to plug that in. I'm going to write this over here so I don't forget. 256 over, I don't want to do all that later. That's 256 over 15. This is equal to 2 pi times that definite integral, which is 256 over 15, minus this definite integral. And so that's the definite integral from 2 to 5 of that times that, which is x squared minus 3x dx. And that's equal to x cubed over 3 minus 3/2 x squared, evaluated from 2 to 5. And so then you plug in 5, you get 125 over 3 minus 27 over 2 minus plugging in 2, 8/3 minus 6. And so that's equal to 125 over 3 minus 8/3 is 117 over 3. (27 over 2 is minus 13.5. And then minus 6 is plus 6. And so that's minus 7.5 there. This is 39. So 39 minus 7.5 is 31.5. Okay, so this definite integral is 31.5. So this definite integral, so it's this one, 256 over 15 minus 31.5. And so that's equal to 2 pi times 256 over 15. Simplifying that is 10. 50, 17 times 15, 255. So that's 17 and 1/15. Okay, so it's 17 and 1/15 minus 31.5. Oh, I made a calculation mistake just here. 3/2 x squared is 3/2 times 5 squared. So that's 75 over 2 here. Minus, that's a 75 over 2. So, okay, that's what I'm understanding. Okay, hold on. This step integral is smaller. Good, that's what we want. The thing we're subtracting is smaller. Good. So this is 125 over 3 minus 75 over 2. And so that's 41. That's 41 and 2/3 minus 37 and a half. Minus 2 and 2/3 minus 6. Okay, so this is equal to 4 and 2/3 minus 1/2, which is 4/6 minus 3/6. That's 4 and 1/6 minus 2 and 2/3 plus 6. And so that's equal to 4, 10, 8 and 1/6 minus 2/3, which is 7.5. Okay, so that's 7.5. Okay, so this is equal to 2 pi. Now, this is 256 over 15, which is 17 and 1/15. Minus 7.5, 7.5. Now we're good. Okay? And so you can simplify that if you want. All right, we'll stop there. That's the value of that volume. We need to calculate that differential. Perhaps if you found the volume another way, it's a shorter calculation. Okay, so we're going to stop there, and I hope this helps.